Hey, good morning.
How's it going?
All right, how's everyone out there today?
Doing alright.
That's good. All right, well, I posted exam grades and comments last night. Let's start with if there are any questions from the exam. We can talk about those now.
Can you show us how to do question 3?
Question 3.
Kind of seems like a lot of people had problems on that.
So question 3, you're walking down a linked list, right? So you're given a sentinel node. It's the usual structure, except it's got this other business inside, this character, and instead of printing the contents of each node, you're adding the data value of each node to a running sum, with the twist that you only want to add positive values. So if a data field has a value less than or equal to 0, ignore it, right? So the picture is something like this. Here's your sentinel node, and it points to a 10, and it points to a -5, and it points to a 15, and it points to a -1, and so on. And so, whoa, what's going on with my camera? That's freaky. All right, and so you start walking down, and you have a running sum. So you initialize running sums to 0. You find a 10. This is a 10. You find a -5, ignore it. You find a 15, this becomes 25. You find a -1, ignore it. And you keep going. And this is a function, and at the end of the function, you return whatever that sum is. So it's, PA3, you have a function that counts how many nodes are in a list. PA1, you had a function that printed the contents of each node in the list. In this question, you were adding the value of the data field for each node in the list, but only if that data field is a positive value, and so not adding the negatives. And it feels like, maybe some people didn't understand what was supposed to happen here, but the reason we were in Zoom was so that, you can ask questions if it's not clear what you're supposed to do. And I think maybe one person asked a question about this, and the same thing happened in the afternoon section, which had a different version of this. So how could we do something like this? So you're making a function named sum, and it's prototyped for you. So it takes an argument of struct node star. So return the sum of the positive nodes. And so we need some kind of, loop to move through from node to node. We also need a running sum, so, integer result equals 0. This will be our running sum. And you can make a temporary variable if you like. You could actually use cent because it's a temporary. You can manipulate it as you like. But in most cases, we make a temporary. Then we call it current. And when we want to navigate a linked list, we begin with what the sentinel is pointing to. And if the list is empty, this will be null. Well, we can certainly set current equal to null. That's not going to cause a problem. If the list is not empty, current would be whatever that first node is in the list. So if it's not empty, it's going to be this node right here. If it's empty, it'll be null. And then our usual loop structure is while the node we're about to work with is not null. And so if current data bigger than 0, result plus equals current data. and then move down the list. And then return result. So this is, our ignoring that. This is our loop that we do, whether we're traversing the list, we're counting the list, we're printing the list, whatever, right? That's how we analyze this current node and then move it to be whatever that node is pointing to. So that assignment statement would change current to be here. And each time through the loop, when we get to the top of the loop, current is pointing to the next node. And you can do whatever you want with it. So in this case, the action is, see if the data field is bigger than 0, and if it is, add it to our running sum. And, it says in there that if there's no nodes with positive values, return a sum of 0. Well, this will do that, right? Because we initialize our running sum to 0. If you never change it, then it will just remain 0. So that's not actually an edge case or a special case. It's if someone says, tell me how much change you have in your pocket counting only quarters. Well, if you have no quarters in your pocket, you would say, I have 0. Because you don't add anything to your running sum in your head. So issues I saw with that, so trying to do something like this, but never, initializing current, or sometimes never even declaring it, right? We do this again and again and again, but it's not magic to the C compiler. It's still just, lines of C code. We have to make sure we tell the compiler, what is current? It's a pointer to a struct node. And what is the value of current? Because if we don't do this, it's going to be null, and we're going to segfault, or we're going to kick out of the loop right away. Right, so you've got to give it a declaration, and you've got to give it an initial value, right, from somewhere. So that was missing. All the usual things that can go wrong. For example, if you initialize to Sentinel instead of Sentinel next, then you need to know if current next is null, and you have to use current next data. And so this is, the thing that I've said. Go through the code, find an algorithm that makes sense, code it, make sure you're comfortable with it. We can, do what we just did, which is say current is the node we are about to work with, or you can stay one step back and say current is pointing to the node we're about to work with. Well, now you have a different condition to check, right? And if you do this until current, if this is current, you want to stop when current is null. If you stop when current next is null, you're going to miss the last node. Because if this is the end of the list and this is current, then at the top of my loop I'll say current next is null. I'm not going to end up processing this node. So those edges can be tricky. And it's a matter of, you can usually find one way to traverse a list, or to loop through an array, or to move through the characters of a string. All these situations have edge cases. You need to start with the first thing, you need to end with the last thing, not skip anything, not too many. So that was an issue in some cases. Some people forgot this part, right? And that's easy to forget, and I forget that sometimes too. And that's, where it's kind of goofy doing this on paper, because if you did this on a computer and you forgot this, your code would never return, and GDB would tell you pretty quickly, what was going on. So I took off a few points for that, but that's an issue. There's logic errors. So in some cases, people, put a curly bracket here and a curly bracket here, which said if the data is positive, add it to the running sum and move to the next node. But if the data is not positive, it doesn't add to the sum, but it also doesn't add to the next node. And so there's an infinite loop. So, just kind of keeping in mind what you want to have happen when. Do we want this to be conditional on this, or do we want this to happen always? And making sure your code is reflecting that. A few cases where people... yeah, that was about it. Alright. I think I took off if people did this, but technically that would give you the correct results. Maybe I owe some people a point back. I'll check that.
If the zero doesn't matter.
Yeah, I mean, it's dangerous to code it like that, because if you want to do something else other than, add that value, and you do it where it's equal to 0 instead of greater than or equal. If you do it where it's greater than or equal instead of greater than, right, it's not doing the right thing. But technically it wouldn't give you the wrong answer in this particular case. So I'll go back and give people a point if I took that off. So questions about this?
Not currently.
Other questions?
Are you going to discuss about the PA3 algorithm? Because right now I'm still working on it, and I'm kind of running into some barriers where I don't know what to do next, or I don't know how to pass strings or copy strings. So I remember talking to someone in Discord about that. I'm still thinking about how would you actually do it.
So let me put a disclaimer out here. There's a lot of chatter going on in Discord about strings and declaring strings and types of memory locations, and there's people from WSU chiming in with things that they're running into and so on. And discussion is great, but most of what's going on in there is really, really far from what you need to be doing to copy strings. So that's my first kind of disclaimer. Is, I like the conversations that I'm seeing in Discord. I like the fact that people are digging into these topics, but a lot of what's being discussed is much, much more complex than what needs to happen for PA3. So let's
I noticed that anyone who would just walk in and look would just be totally confused.
Yeah, if you just kind of come into it, you're going to think that you're trying to land a person on the moon or something. And there are lots of, details to this that will come into play, on later assignments, especially at a university. But let's look at copying strings from the perspective of PA3. So let's just think about passing strings back and forth. And so I'm just going to pretend that we're writing a find name function, which we pass it a string that we want to have filled in with information, and this function is going to somehow, I don't know, pull the name from a database or something and load it in. It's not going to be that fancy, but that's sort of the essence of what we're going to imagine this is doing. So let me prototype my function. And I'm going to declare the argument as a car pointer, right? Because when I pass a string, strings are pointers to characters. Arrays of characters are pointers to characters. I don't want to say car bracket 120. I don't want to say car bracket bracket. This is just a car pointer. All right, so I'm going to pass a car pointer to this function. And because it's a pointer, this function is going to be able to change the stuff in the area of memory that this thing points to. When I call find name, what am I going to pass? I'm going to pass the address of the first character of this array. Because name, N-A-M-E, means the address of name bracket 0. And that's
I have a question.
Yeah.
You said that when we, return, or we have to malloc for the size of the first and last name, right?
inside your code for making the lists and the hashes, yes.
But when we search, we're gonna just have a set length for the input in our fgets, right?
So yes, so you're told that the maximum length for any of these fields is 256. So you can make your strings, 257 in length and feed those into scanf. And your fgets can be something that's, 771 characters or longer to hold the entire, 3 fields with spaces in between.
I'm just saying for when we search, like when we type in a license plate number, that fgets.
Mm-hmm. Yeah, that does not have to be bigger than 257.
Okay.
Because that's the longest license plate. So yeah, most everything in your main program, string-wise, you can just declare like this. And that's statically allocated. It's automatically, released when the program exits. It doesn't create memory leaks. What you have to do with malloc is when you're creating a new node in your linked list, it's got a field called plate, and you do not want to make that 256 characters. You want to make that big enough to hold the particular license plate you're storing, but no bigger. Alright, so here's my find name function, and we're going to do some stuff. And then, eventually it's going to find a node that has, the matching license plate, for example, and it's going to copy with string copy from the name field of that node to the argument that was given to this. So I'm just going to, string copy a string here. But it would, walk down a list and compare and all that kind of stuff. But our goal here is just to be able to load a value into this argument and convince ourselves that we can get to that argument by simply passing this. And this should work perfectly fine. Include string if you're going to do string copy and string length and such. Right, so my main program is able to access that string that was copied into it in that function, the string hello. And that's really all you got to do in this whole business of like calling. Let me pull up the actual names here. So calling hash find from your main program, you're going to pass, a car plate bracket 300, a car first bracket 300, and so on. You're going to declare those in your main program, pass those as arguments for first and last, right? Plate should be whatever plate you're looking for, so that's the thing that you got from the user. And then if this returns a 1, you know that the first and last name variables that you passed have been changed, and this function has loaded the actual first and last name corresponding to the plate into those strings, and then you can print them out or do whatever it is that your main program wants to do. So if the string passing is causing problems, forget about the hash, forget about the list, work on something like this. And get the mechanics of how you're going to pass strings, how you're going to supply a field to load a string into, and so on and so forth. Get that nailed down with your own sample code. Something that lets you work out these details without also trying to figure out how to read from a hash, how to walk down a linked list, and all that kind of stuff. And then once you have these mechanics, go ahead and use them to write, the hash find, but initially the list find, which is the thing that actually does the work. And hash find is really just a call to list find. And there's other ways you can write this thing that's on the screen right now that will work. And those ways are not wrong, they're not better, they're not worse, right? But this way will work. And if you want to experiment with other ways to do it, that's fine. Just be aware that you know, you have a way here which will work, and other ways that might seem comparable or similar or reasonable actually might not. And I always think it's good to try different approaches to things, and to try to understand, you know, why one thing works and one thing doesn't. But you know, as long as you're aware that's what's going on, right? That's what you're spending your time on. That's good. So if I do this, right, that's going to segfault because I'm not allocating space. I can do a malloc, and that should work fine. I could try to do this to allocate space. Right, that's also going to segfault because when I allocate space like this isn't a non-writable area of memory. If I run it in GDB, though, it may not segfault, because when I run things under GDB, sometimes things are put into different locations. So do it like this, you should be fine. All right, other questions on this or on the midterm? And I still want to talk about how to parse command line arguments and how to ingest the flat file, so I'm going to do that regardless. But any other questions?
What was it? I missed the question on the exam. Give me a sec.
Okay.
Oh yeah, the one question I missed was question 1D that I got wrong. What was the? I don't know. Could I just get the right answer on that?
1D.
Exactly was. Oh yes, write a declaration for an array of unknown length. Yeah, I have no idea how to do that.
Oh, an array of unknown length of struct access named all records. So if you want an array, struct access star all records. And it's the same thing. If you want an array of integers called data, you say integer star data.
Hey, that's my only question is struct access star all records. That's the same way that we declare, say, it's just another struct. That's the same as access.
That's a pointer to a struct access, which is different from saying this, where all records would actually be a structure containing those fields. This is simply declaring a pointer. It's just going to be a memory address. But the compiler will expect it to point to a struct access, which means it'll be pointing to something that has those, you know, start, middle, end fields and so on.
Okay, so declaring an array is the exact same as just declaring a single pointer to a struct access.
Exactly, yeah. Just
so
like...
It's the exact same as in PA2.
Yeah, so just like when you do this, am I declaring a pointer or am I declaring an array? There's no way to know because there's really no difference. And I might just be planning to pass data to, you know, scanf or pass it to a function where I want to change its value. Or I might be planning to say something like, you know, data bracket I. And both of those are legal and legit, and there's no difference in how I would declare this, whether I was just thinking of it as a pointer to one integer or I was thinking of it as the name of an array containing 1,000 integers. No difference. And that's just the way, I'll say, kind of weird way that that C handles arrays. And some people did something like this. Struct access star star all records. And this is saying that all records is a pointer to a struct access. So this could be a two-dimensional array in some sense of struct access. Like when we say car star star argv, it's a two-dimensional array of characters or a one-dimensional array of strings. Or this could be an array of pointers. So if we had an array of sentinel nodes where each node was, a struct access, we might declare it like that. And so our hash table, we're actually declaring a struct node star star, all records. And I think that double star only cost a point. But and so some people did something like struct access all records bracket bracket. And yeah, so thanks for bringing that up. So this is not kosher for C. Right, if I try to make an array like that, right, I will get a compile error. It will not even compile. So if I do this struct node data bracket bracket, right, that will not compile. But I've saw a lot of people doing this, and I've seen a lot of people talking about this in Discord, and so rather than take off the point for that, I wanted to talk about that in here, right? I don't know where this came from, but this is not valid C syntax. Now I can do something like this, right? I can give it a size, and that'll compile just fine. Or I can give it no size and make it, something general like that, and that'll be fine. But that does not work. Now there's cases where you see this in arguments to functions, and that's like a special thing that's allowed to say, hey, I've got an array coming in, I don't know what the size is. But as a variable declaration, that's not valid syntax. And again, I mean, if you're a real, lifelong fan of empty square brackets, okay. But I would say you never need to do this, right? If you want something that points to a type of variable, or if you want an array of a certain type, you can always get away with doing star if it's not actually going to be given a memory location, or doing this if you actually know how much space you want and you want to allocate that memory right there.
Could you set it equal, or could you validly do struct node data open bracket num close bracket, and then initialize like num as an int, and have it be initialized as equal to null, and do it that way?
So sometimes this works, right? And I know I shouldn't pass an int to main, but it'll compile just fine. It'll compile the same regardless, right? And I believe the compiler will make this work. And so you can do that. But I think if num is something that's going to be calculated at runtime, I don't think it can do this.
See, that's why I figured you'd make dynamic arrays when I first started doing C. But it doesn't work, right?
Right, so this is going to definitely say, tell me how big a struct node is, however many bytes that is, multiply by num, that's how many bytes I need for num of these struct nodes, allocate that much space, and have data point to it. And that's I think the cleanest, most portable way to do this. And this is just C, right? When we get to Java, we don't have to do any of this business. We never do a malloc. In Java, we'll be able to, use a variable in the declaration of an array and so on and so forth. On the other hand, in assembly language, we absolutely have to do a malloc in some way, shape, or form. And C is, this high-level version of assembly language. So the things we learn to do in C, like this, translate very, very easily to assembly language or machine language. So if you're ever doing, embedded programming, if you're ever doing real-time programming, working on control systems and so on, you'd be working closer to this kind of level. Whereas the things that we learn in Python and Java and all this other stuff, right, works great in a higher level part of the system. Integer num equals null is definitely not going to be something good. Struct node data bracket num. If we don't declare, so someone's asking about something like this. Let's get rid of this. So this is going to make the compiler really unhappy because it doesn't know anything about num at that point of working through the program. And this is going to throw a warning because null is a pointer and num is an integer. And if we put this first, this would try to declare an array of size 0. And I think that would be confusing to it. But that's going to give us a few things. So yeah, declaring a variable is just, struct access history with no asterisk. Allocating space, history equals malloc size of struct access. And then history, so if it's a pointer, so struct access star history, and then history equals malloc. And then history arrow start, arrow middle, arrow end equal -1. And then this is a declaration, and then to make an array of 100 of them, so you could make all records equal malloc, 100 times size of struct access. And I don't know what it will do with this. Well, let's get rid of that. So it doesn't like the fact that it's a pointer going into an integer, but it seems to accept that, and I think this is declaring, something like that, an array with no memory associated with it.
Because I'm putting it in no because it's because it'd be like yet to be defined length.
Mm-hmm.
Right.
So can we assign something to data after we've declared it to be an array like this? And does not seem to like that because we declared data to be an array type, and it doesn't want us to change what data points to. So I think once you do this, right, we can get rid of this. I think this is perfectly legal syntax, but I'm not sure you can do anything with data after this because it's not going to let you change it. And I think this is similar to, if you say integer d bracket 10, I don't think I can change the value of d at that point. right? It's pointing to this array, and my compiler will stop me from being able to change what D points to. And I think that's what's happening in here also. So you can do this, but I don't think data is usable for anything.
So how would doing struct like struct node star data be any different? Like we're using that to declare an array with an unknown length. How would that be different from, or how is that different from just declaring a node?
Because once I put the bracket 0 here, I've said data is an array of this many elements. And for whatever reason, the compiler does not want to change that declaration of data. But when I do this, I'm not changing the nature of data. Data is a pointer to a struct node. What struct node is it pointing to? Well, the one that Malik returned. And then I can choose to treat that as an array if I like. If it's more than just, a pointer to a single struct node. But the purpose of this declaration is to say, hey, this is going to be a pointer or this is going to be an array of these things, without actually declaring, what it's pointing to. And it leaves it up to you to, at some point, define what the value of data is, what the thing is that it's pointing to, what location in memory it's pointing to, which is what this does. And so like that, it should compile fine.
Okay, that makes more sense now.
Okay. It's pretty quirky, and especially if you've done programming in other languages, it's pretty archaic, right? But if you think of it from the perspective of assembly language, if you think of Engineering 270, if you've done that yet, it makes it a little more forgivable, because, ultimately at the machine language level, this stuff has to happen. And in nicer languages like Java and stuff, languages that make things more convenient, this stuff happens automatically when you do something like, struct node data bracket n, All right, good. Other questions? So question 2, didn't see a whole lot of difficulties with, and this was just keeping track of what's pointing to what. So if this is list, right, the Sentinel node, list next is this field down here, but list arrow next is saying, this address of the node over here. So we could label the second box list arrow next. And if we say list arrow next, arrow data, we're talking about the data field of this. If we say list arrow next, we're talking about the value of this field down here, which is the address of this node. And then if we say, that thing arrow data, then we're talking about the data field of this node. So this prints a 400 followed by a -1. And really good work on working with these questions for deleting and inserting new nodes and so on. I saw a lot of people use temporary variables, and that makes things just a whole lot easier, especially when you're working under a time crunch. A lot of people gave this thing a name and this thing a name and this thing a name, and then if you want to delete the 123, well, you just take this thing, set its next equal to null, and then you free whatever you called that thing. And if you want to insert between here and here, you make a new node, you have its next equal to whatever you called this, and whatever you called this, you set its next equal to your new node. And it's a whole lot simpler than trying to figure out, list arrow next, arrow next, arrow next, arrow such and such, right? It's often a good idea to use temporary variables, and so a lot of people did that.
I have a question.
Mm-hmm.
It's not really related. It says my midterm was late, which is interesting. I know it wasn't, but it just says it was. So.
How late did it say it was?
I have no idea. It just says, oh, never mind. I know why. Never mind. Sorry.
Okay.
Just because I turned in my signed version after.
Oh, that's right. That's right. Yeah.
Yeah, never mind. My bad.
No problem. All right. Let me see. Let me see something.
Quick side question for PA3 before we start talking about the things on the agenda for that.
All right. Can you hold 1 second? Because I want to. I want to pull up a question from chat. Da, 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 da. So what is this going to print out? If I do size of data bracket 100.
8 or something.
It's not going to print out the size of that array for sure. It's probably going to print out. It's probably going to print out the size of an integer, which will be 4. Right? And if I do something like this, and I try to print out size of data bracket 100, it's probably going to segfault. Nope, it returned 4. Oh, that's interesting. Right? This is not saying what's the size of an array of 100 integers. Right? It's saying what's the size of the 100th element of this array, which is a single integer. And so question in chat why I marked down for improper syntax. I don't think it was for improper syntax. I think it was for oh, I didn't mark you down for improper syntax. Yeah, because I saw so many square brackets and I decided to talk about it in class. All right, let's see. All right, global variables. Yeah, global variables have to be declared outside of all functions. If you're doing it in your main program, it should be outside of main, but I would not do globals in your main program. And you should definitely not write your code in a way that requires a global in your main program. But in your, hash.c, for example, or whatever file you're writing your hash function in your hash, functions, you would declare, integer hash size. And then you could, you know, start your functions and list them after. But yeah, putting this outside of any functions makes it global within that file from that point on down. And so all the functions you write after that have access to that variable. And so for the hash table, that's the place to put it. All right, and I don't know if that was the question that you had, but there was a question. Was that it?
Yeah.
Okay.
Was, I think, was Joseph in the chat.
Cool. All right. Well, let's talk about command lines. So we're writing a program named plate, and there's a few ways the user could try to run this. They might just say plate. They might say plate followed by a file name. They might say plate followed by a file name followed by an integer. They might say plate file name followed by you know, junk, something that's not an integer. Or they might say plate followed by other stuff, right? And so which of these are legal? Which of these should we continue doing some work on if we detect that's how the person ran the program? This is PA3.
Wait, you can call it just plate?
That's my question. Which of these are legal? You can type anything you want. It's a free keyboard.
2 and 3.
2 and 3, good, thank you. So these are the only legal ways to run your plate program. And this is an error, this is an error, this is an error. And so the first thing you want to do, probably, one of the first things, is figure out, you know, do I have any work to do? Did the person give me a reasonable task here, or should I just yell at them and exit and go back to sleep? So one of the differences is, you know, this thing only has the name of the program. There's nothing else after it. This thing has too many things after it. So if we declare our main program like this, what can I do to know if the person typed this? How would I recognize that situation? And take a shot. If you're off by one, it's not a big deal. There we go. Cool. All right, so how do we use argc and argv?
So I don't know, we check our C to make sure it's equal to 1 or 2.
Yeah, so
It's actually 2 or 3, right?
yeah, so whether it's, you know, 0 or 1, it only took me about 30 years to finally commit that to memory. So you know, you can always write test code and try it, but if I'm remembering it correctly, in this case, argc will be equal to 1. Right, saying, hey, there's one thing on the command line. So if argc is 1, I'm done. I can just say, hey, you know, you gotta give me a file name at least. And in this case, argc is bigger than or equal to 3. And if I see argc bigger than or equal to 3, I can say, hey, what are you trying to do here, you know? You only get 2 command line arguments, and I can exit. So I only have to worry about, you know, the possibility of this. Yeah, go ahead.
didn't hear anyone say anything.
Okay. So if argc is 1, not enough arguments. If argc is bigger than or equal to if argc is bigger than 3, too many arguments. So if argc is 2, right, I've got a file name, and I go ahead and I pass that to whatever is going to, you know, open a file and read it in and build a hash table, and I use a hash size of 100 because that's the default. If argc is 3, I still have the possibility of, you know, maybe they didn't give me a valid integer. And so this argument right here, this is argv bracket 2. And so how do I know if that's a valid integer? Well, use scanf. So if argc is 1, error. If argc is bigger than 3, error. If argc is equal to 2, set the hash size to 100 and process the file name. If argc is equal to 3, then try scanning argv bracket 2, see if it's an integer. If it is, process the file name with whatever that integer is as the hash table size. If this is not an integer, that's an error. So you can make yourself kind of a decision tree, you know, to move from the beginning to either printing an error message and exiting, or, you know, going ahead and opening a file, reading it in, building a hash table, and then continuing. But again, you know, go ahead.
Sorry. So if I'm reading this right, we make a function separate from main and then call it in main at the start of the program?
To do all of this?
Yes.
You could, or you could do this right in main. It's a relatively simple enough set of possibilities that if you put this directly in main, I don't think it's going to you know, make your code overly cumbersome. If you want the practice of, you know, passing things to functions, you could make a function. And you could make a function that returns, you know, the hash table size, or, you know, -1 if there's an error, or things like that. But I would probably just go ahead and put this directly in main. Alright, so test code. So no arguments, argc is 1. 2 things on the line, it's 3. 3 things on the line, it's 3. And 4 things on the line is 4, and so on.
I can't remember. Don't we have to? We don't have to use fgets, do we?
Not for the command line arguments, no. Those are coming into your main program through these arguments, and so there's no fgets there. You can do all of this without asking the user for any input. And the only time you're going to use fgets is after, you know, you've done this, it's all valid syntax, you open the file, you read it in, you build a hash table. Now you go into your main loop and you wait for the person to type in a license plate. That's where you're going to use fgets. And I think that's the only place in the whole program.
Your program doesn't have to print out the each thing of data, like when it's building a hash table, right?
No, and you can do that when you're debugging, but definitely don't do that for the final program. But it's a useful thing to do when you're debugging. And let's review how to ingest a file. And the main thing that you're after here is fopen. That's sort of the biggest new piece of this compared to just reading from standard in. When you want to read a line, guess what? You use fgets. Well, you've been using that since day one. But it's you know, the thing you normally do after you fopen a file. And then there's an fclose, which is kind of a formality, but you still want to do it. But really, fopen is the only kind of like significantly new piece to all of this. And so it's got a manual page, comes from standard I/O, and fopen basically takes a string that tells you what file you want to open, and then it takes another string, which is the mode, and it returns this thing of type pointer to an uppercase file.
How do we error check that file? Do we just open it and see if there's something in it, or?
So you can open it and save the value that fopen gives you back, because that's what we call the file pointer. But if you look at the return value, fopen may fail, may fail. Return value. Null is returned if there's an error. So the value that fopen gives you back will normally be something non-zero, because it'll be a pointer to a thing of type file, uppercase. But if there's an error, it'll return null. And so we can do something like this. So let's just open a file and print its contents. So we'll write a version of cat here. So I'll make a file star fp. This will be returned by fopen. So I can say fp equals fopen. Well, let's do this. Let's open data.txt. We'll start with that. And the command, the mode that you pass to this, is one of these. And for this, we're just going to open the file for reading. We don't want to modify it. You don't actually have permission to modify it. It'll give you an error if you try. So we'll open the file for reading. That's just an R. But this argument has to be a pointer to a character, so it's a string. It's something inside double quotes. So we'll do quote R. And then normally we do this, right, to read from standard in. The only difference is we're going to read from FP in this case. That's what I'm going to declare it as, just for kicks.
Oh, are we going to put this in a while loop then, or something like that?
Yeah. So let's just try this simple version first that just does a single fgets and then closes the file. And if I do this, I'm going to segfault, right? For the simple reason I don't have a data.txt in my directory. So we'll put some data in there, and now if I run this, it tells me, hey, I read a line from my file. The line was, this is a test, followed by a new line. If I do this 3 times, right, it reads 3 lines from the file. If I do this 4 times, well, that last line gets read twice. Right? The file only has 3 lines in it. And so if I read these 3 lines and then I do another fgets, well, fgets is going to fail and my buffer's not going to change. So I'm going to print that line out twice. So,
Code real quick.
say again?
Could you go back to your code?
Yeah.
So you don't even have to change. The fget will just read the first 1024 and then read the next line
It'll read
automatically?
it'll read up to 1024, but if it encounters a new line, it'll stop and come back.
How does it switch to the next line of the file is my question.
It reads up to and including a new line, and then it comes back, and the next time I call fgets, it continues where it left off. And so this file,
Oh, okay, right.
right, this file is really just, a bunch of characters that happens to have new lines here and there. So the first fgets reads up to and including that character A, that's a new line, and then the next call continues from here and reads 68, 61, 68, 61, 0A, that's the ha-ha. And then the next one reads BYE in a new line.
I see, okay.
Why is the greater than sign that's like in each printf being put on the new line even though it comes before the new line that stayed there?
Because the first string that it read was, this space is space A space TEST new line. So all of those characters, including the new line, character 10, are in this string called buffer. And the print statement says print a less than, followed by the string, followed by a greater than. So there's the less than. This is the string. This is a test followed by a new line, which came down here, and then this was the greater than sign at the end.
Oh, okay.
And this is why I keep saying put delimiters around your strings, because if we just printed out buffer, we'd see an extra space in here, but we might not realize that there's actually a new line there. Let's see, section 1.1, number 2 of PA3. Number 2 of PA3. Yes, you have a maximum of 256 characters in the plate, 256 characters in the first name, 256 characters in the last name. So in your main program, when you're declaring those arrays, you can just make those, car, plate, bracket, 256 or 257. But when you're making a node for your linked list, don't define the node to be something containing an array of 256 characters. The node has to be declared like this. Plate has to be a car star, first has to be a car star, last has to be a car star. And then you allocate space on the fly. So I'm giving you that maximum length to simplify the main program, but I don't want you to also use it to simplify the coding of the linked list by just allocating a ton of space for every field.
I see. Very interesting.
I was trying to
Oh, I see. There was a previous question. How large a file name should we account for? Don't worry about the file name. I'm not going to go crazy on you. I mean, make it 1024, you're fine. If I've got time to type in, 1025 character file name just to try to break your code, I'm probably in the wrong business. So it's a fair question, but don't worry about it. But the reality is you do not need to allocate any space for file name. That's probably the better answer, because the file name will be in your argc array, your argv array, and that is something you can pass directly to fopen, for example. So yeah, you shouldn't need a separate string variable for the file name. So that's the better answer.
Even if you pass it to a function, you can just use char star and you don't need to allocate it in that either.
Right, if you pass it to a function, declare the argument to be a car star, and it will be pointing to the same, hefty chunk of memory that's already been set up by bash when you executed your program. And it's really the operating system or bash that's allocating the space for that command line argument. All right, so let's clean up this program here. Let's check the file pointer. So if the file pointer that we get back from fopen is equal to null, we'll print an error message saying can't open. And I'm going to be, a little verbose here. I'm going to say can't open %s and I'll put out the name of the file. So if we remove the data file and we run main, instead of giving us a segfault, it now says can't open data.txt. And then if we want to make this general, if we want to open a file that's named on the command line, like when we run the plate program, instead of opening data.txt, we're going to do argv bracket 1. And then down here we can print that out in our error message. And so if I say main haha, it says can't open haha. If I say main.c, it'll open that up and print it out. And then there's this lingering problem, which is if we just say main, we're going to get a bogus error, can't open null. That might segfault actually in other cases. So what do we want to do here? We need to go back to this business of, did they do this or did they do this? Well, if they do this, argc will be 1. If they do this, argc will be 2. And so in the very beginning, I could say something like this. Alright, so if argc is not 2, that's the wrong number of arguments. And we're just going to exit. We're not going to do anything else. Otherwise, we'll go ahead and we'll try to open the file. If we can't open the file, we'll print an error and we'll exit. We won't do anything else. Otherwise, we'll go on and start doing some fgetting and some reading. So if I just say main, that's the wrong number of arguments. If I say main with too many things, that's the wrong number of arguments. If I say main with 1 argument, it will try to open it, but if it doesn't exist, it will fail. And if I say main with the actual name of a real file, it'll open it up and start printing the contents. And again, the order of these is important. If I put this check down here, my code does not work. Because if I say main, it's going to give me this weird can't open parentheses null issue, right? If I want to know if I have a file that I can open, I have to check that condition before I try to open it. So this is the thing I keep, telling people in 224. Always check argc before you use argv. Right? Don't try to use argv1 unless you know that that actually exists, and you only know it exists if argc is at least 2. I lost my chat window. Let me get it back. Alright. Alright, and then the last business is being able to loop on all of this. So instead of, calling fgets bunch of times, we can say, well, fgets does not return null. And so this says call fgets. If there's anything available to read, read it into buffer up to either a new line or 1024 characters, and return something non-null, which means this will not be equal to null, so we'll continue with the loop. If fgets reaches the end of the file and you try to read beyond it, this will return null. This while loop will fail, and it will exit the loop, and then we'll close the file. So there's our whole file. And so we could write our own version of cat if we wanted. And these new lines at the end, they usually don't cause us trouble. They might cause you some trouble in PA3. So how do we get rid of those trailing new lines? Well, if you do an fgets and you type HELLO and hit enter, here's what's stored in the string. The stuff that you typed in, a new line character, which was where you hit enter, and then an all terminator. What we want to do is we want to get rid of this new line, and this is, in this case, at index position 5, because we start from 0, so 0, 1, 2, 3, 4, 5. And if we look at the string length of this string, it's going to be equal to 6, because we have 1, 2, 3, 4, 5, 6 characters before the null terminator. So the character we want to get rid of is at an index 1 less than the string length. And this is that edge thing that we always get with arrays. If you have an array of 10 elements, right, if the length of the array is 10, the index of the last element is 9, because we start from 0. So this new line is always at string length of the string minus 1. And you can run experiments or do this on paper to make peace with this, and it's an important thing to make peace with. But once you've done that, if you want to get rid of that new line character, we can do something like this. Right, this will take the number of things in the buffer, the string, subtract 1, that should be the index of the last character of the string, which is the new line, and by changing it to a \0, what do? I replace this with a \0. Well, that ends the string right there, and now my string just looks like HELLO without that new line. And so now if I run this, I need my string again. Now if I run this on a file, right, I get 1 line per output. And my line begins, right here, and it ends after the last character of the line. We've gotten rid of that null terminator. I think you could modify the cat command to do that, which would be pretty awesome. I think you could make your own script named cat that would either use /bin/cat or print out a message if there's no argument. That would be funny. So if you wanted to do something like, you know, print the contents of a file with line numbers, I can make a line number, and in my print statement, I could do something like this, right? Initialize a variable to 0, and then on each line that I print out, I'm going to print out plus plus line num, so I'll add 1 to it. So my first line will be number 1, and I'll print it out with a %04d, which will put leading zeros in there, and keep everything nicely lined up. And now if I do that, you know, I've got a way to print my file with line numbers in the front. And so you can kind of go to town, you know, and just play around with this kind of stuff. If you want to practice manipulating strings, if you want to practice doing file I/O, if you want to practice with command line arguments, right? You can do what we just did here in a million different flavors, and you know, get as comfortable with these things as you like, so that when you're trying to do hash tables and linked lists and all that stuff, you're not also fighting with, you know, seg faults because you forgot to check argc or things like that. So go back and refresh on this stuff, and it'll be helpful. Alright, we're way past our break time, so let's take a 5-minute break and come back, see if there's any other questions on midterm or on PA3, and if not, then we're going to go back to talking about trees some more. So let's come back at 11:23.
Good. I'm Valentine's Day shopping, and I got belt and suspenders.
Oh, cool.
Yeah. And now I'm looking for unscented hand sanitizer to put on backpack, unless you've got one of those.
I don't.
The only one she has is scented, and she never wants to use it.
Yeah, mine's are stinky.
Yeah.
And they also feel like they're ripping the skin off. So they're like thick and globby. Hello, Bart.
Oh, we do have a Bart.
Apparently.
There are lots of Barts.
Mini Bart.
They're all Bart.
I think I heard a bird flying in the window.
I wondered what that was.
Yeah.
Again, man? What is it with this window?
Oh, no.
Oh my god. That's one of the orange ones. How are they getting this window? I don't understand.
Alright, we're back. We have these, this pair of beautiful orange birds around here. And I heard something hit the window earlier and I just went to check and it was one of our orange birds. And that really sucks. Yeah.
Is it still alive?
Not at all.
No?
No, its neck is broken.
Oh. Do you guys have bird feeders or something?
Yeah, there's a bird feeder in the back of the house. And, we've had 2 birds hit the front window for some reason, so we're putting stuff in there to try to distract them away. But that's a drag.
Yeah, we have a bird feeder, and I think they hit our window.
Yeah.
They quit. Now it's been there for so long.
Yeah. That's a bummer.
I'm gonna bury them unless you think I should. Wait.
Yeah, I was gonna wait,
Okay.
but definitely before she gets home.
Yeah.
Yeah. All right. Let's see. So other questions.
How do we go about, so for when we're fgetting, or not, yeah, we'll use fget, right?
Mm-hmm.
When we're using fget on the file, there's going to be 3 space separated things, right? And
Mhm.
do %s space, %s
Right.
space. Okay.
Yeah, so you can scan those into 3 strings.
Okay. Ooh. When we do that scanf, that's when we use malloc, right?
So you don't need to use that for scanning. So assuming you've done your fgets, you can do plate, first name, last name. Where before you do that, declare these statically. And just make them big. And then, whatever you have on that input line, the stuff before the first space will go into plate, the stuff between there and the second goes here, the stuff between the second and the end of the line goes here. And you could check this, make sure it returns 3. I think in almost all cases it's going to return 3, unless maybe there's an empty line in the file or something. But you could, just do that as an extra check. I'm not planning to run your code with a corrupt database file, but, for completeness, you could check to see if it returns, if it actually matches 3 fields. But yeah, this will, load those into these 3 fields, and these can be statically declared. And then you can pass these to your hash add function. But then inside hash add, it's going to call list add, and inside list add, it's going to make a new node, and then it's going to do malloc to set up space for the plate first name and last name fields of that node.
Okay.
And of course, if you don't want to do this, if you're working on the hash functions, just call hash add. And pass it. I think you have to pass it the hash table too, but you can just pass.
Get the index and then calls list add with that index, right?
Yeah, so hash add is, table. And then plate first name, last name. You can just pass those as quoted strings if you want for the sake of debugging. And then hash add takes the plate, runs it through the hash function to get an index, goes into the table and grabs the element with that index, and then passes that as the sentinel node to the list add function. And it passes the plate first name and last name to list add.
Wait.
Want me to say that again differently?
Yeah. Search for the given plate. Download the matching.
So hash add.
Oh, hash add.
So you got a table, plate, first, and the last. Alright, so index equals hash plate.
Your computer screen is in the way.
Yeah,
So-
I wonder if he's supposed to be showing.
So hash the license plate to find the index in the hash table, and then sentinel node equals your hash table, bracket that index. So this is where list is stored. This is the sentinel node of the list. And then you can go ahead and call your list add function with the sentinel node, the plate, the first name, and the last name. That's pretty much your whole hash add function. There's no real work happening inside here, right? It's list add that actually does all of the, make a node, allocate space, all that kind of business. This is just figuring out which list should we add it to, and then calling list add for that list.
Thank you.
Mm-hmm.
Using sent for sentinel node always kind of knocks me off for a little bit.
Yeah, so I mean, without trying to be goofy, right? You could call this, sentinel of list to add to, and that would not be an unreasonable variable name, right? So index of list to add to equals hash plate, sentinel of list to add to equals table bracket index of list to add to, right? Hash table, not just table, right? But if you use descriptive variable names, then the actual C code sort of becomes a little bit self-documenting, right? Sentinel of list to add to equals hash table bracket index of list to add to, right? Well, that kind of unwinds itself for you as you look at it. And then list add, and I'm passing the sentinel of a list I want to add to, and then I'm passing that information. So don't be afraid to be more verbose. All right, well, let's talk about more of this business of recursive tree operations. And so, I think we talked about printing a tree, and we said if we had a tree like this, and we wanted to print the contents of that tree, in other words, print each node, we only had to do three things. The first thing was to print the root node. The second thing was to print everything in the left tree, left subtree. And the third thing was to print everything in the right subtree. If we do those three things somehow, we will have printed everything in this tree, because the whole tree is comprised of a root and a left and right subtree. That's everything there is in the tree. So I can make a tree print, and I'll pass in, the root of a tree, and I could say print root data tprint root left and tprint root right. And that's 90% of a complete tree print function. Print the root, that's A. Print everything in the left subtree, that's that stuff. Print everything in the right subtree, that's that stuff, and we're done. And the one thing we have to add into this to make sure we don't segfault is, you know, when we try to tprint this tree, we're going to print the root, we're going to tprint this and this. When we try to tprint this, we're going to print the root, and we're going to try to tprint what's on the left, which is null. So this will eventually call tprint with an argument of null, and if root is null, trying to do root arrow data will segfault. But if root is null, we're being asked to print everything in a tree that's completely empty. There's no need to do anything. So we're safe to kick out of this function as soon as we detect that we've been called with null. So there's a 4-line tree print algorithm. If the argument's null, return, otherwise print the root data and then tprint the left and right children. So let's look at what an actual tree node might look like. So let's do a struct t node. And I've got letters here, but you know, we always pick on integers, so I'm just going to pick on integers. So I'm going to have a field called data, which is an integer. And then I need to know who my left and right children are. Well, the nature of this tree, again, is that, you know, this is a tree, but the thing on the left is also a tree. And when we want to deal with a tree, what we do is we deal with the pointer to its root. So this whole left subtree can be accessed by simply having a pointer to the root of that left subtree. So we're going to have a field called left, which is going to be a struct t node. Star left. And a struct t node star right. So that's for now what the nodes of our tree are going to look like. And they're going to be these structures with a data field and then left and right pointers to other tree nodes. And the fact that this is pointing to a whole subtree is not really relevant to us. All we need to know is that this thing is pointing to a node. That node, of course, is going to have some data, and it's going to have a pair of pointers itself. And the things it points to will be nodes, t nodes, which will have data and also have pointers to other t nodes. So into this structure is built in this idea of, you know, this bifurcating branching network. But we don't really need to worry about it like that. All we need to know is that, you know, the left child of this is a pointer to a tree node, and the right child is a pointer to a tree node. And then the actual code for a tree print function would pretty much be this. We need to declare, you know, what type of argument root is, but this is pretty much the actual C code. All right, so let's talk about node order. And what we call a BST, or a binary search tree. And so we've been talking about these binary trees, but in a little bit of an abstract sense. We've just kind of said there's nodes, there's a single root, things have children. If it's a binary tree, there's no more than 2 children. But there's an extra characteristic we can put on a tree And this characteristic makes a tree a binary search tree. So we have the following property in a binary search tree. Given any node, let me call it n, everything in the left subtree is smaller than n, and everything in the right subtree is bigger than n. Alright, so let me put a little footnote here about terminology. When I say one node is bigger than another node, what I mean is the data value of one node is bigger than the data value of another node. So when we talk about everything in the left subtree is smaller than n, what we're really doing is comparing data values. So for example, n arrow data. So that's the first thing. And rather than constantly saying the data field of each node in the left subtree is smaller than the data field of the node n, we'll just say the left subtree, everything in the left subtree is smaller than n. But that's what we're actually talking about, is comparing data values. And so these are the kinds of trees we're going to work with from here on out. And let me draw a tree you've seen before. And why do I keep drawing this? This is an example of a binary search tree. And you can see if this is true by picking any node and looking at everything in the left subtree and the right subtree. If I look at this 20, everything to the left, which is just 10, is smaller. Everything to the right, which is 30, is bigger. If I look at the root of this tree, 40, everything over here is smaller than 40. Everything over here is bigger than 40. If I look at the 60, everything over here is smaller than 60. Everything over here is bigger than 60. So this is an example of a binary search tree. And it's a binary tree, which is all the stuff we've said about trees, but with this one extra characteristic, that if you look at any node, everything to the left is smaller, everything to the right is bigger. All right, everybody got that?
Yeah. How do you code to create one of these things?
Oh, we'll do plenty of that probably Wednesday. But first I want to talk about searching a BST, and when we talk about searching, we'll actually see a hint on how to create a BST. So how do we search for something? Suppose we want to find the number 50. And remember, a tree, we're just given a pointer to the root, so this is really all we start with, is just this 40. And we're looking for a 50. Well, this is not equal to 50, so we can't say yet that we found a 50, but we're not ready to give up. And the normal problem with searching a tree is you've got two directions to search. And you know, if I come down here, then I've got two more directions to search, and I might have more directions after that. And if I don't find anything over here, I come all the way back and remember, oh yeah, I could have searched over here first. And it's this problem that grows more and more complex the bigger the tree is. But with a binary search tree, we don't have that problem. Because if I'm looking for a 50 and I look at the root and the root is 40, what can I say? What do I know? Think about playing high-low. How did my life just get simpler?
It's greater than 40, so you would look in the spot where you reserve numbers greater than.
Exactly. The number I'm looking for is 50. The root of the tree is 40. 50 is bigger than 40. In a binary search tree, everything to the left is smaller than the root. So everything over here is going to be smaller than 40, and 40 is smaller than what I want. I can eliminate that entire half of the tree. Don't have to consider it at all. So I had two directions I could move from my root, but I don't have to look at anything to the left, because I know all of that stuff is going to be too small. So I only have to move to the right. And now I get to the 60. Well, that's not the number I'm looking for either, but guess what? 60 is too big, and everything to the right of 60 is going to be bigger than 60. It's also going to be too big. I can eliminate all of that. And now I just check this subtree to the left. And I check to see if that's got a 50, and hey, that's what I'm looking for. There's the 50, I found it. And I never looked at the 20, the 10, the 30, or the 70. Right? This is high-low. This is basically cutting our problem in half each time that we do a comparison. If I was looking for a 30, I would say it's smaller than that, throw away all of this. Look for a 30 compared to that, it's bigger than that, throw away all of this, there's my 30. Alright, so everybody see the idea of searching? So what's going to happen if I search for a value that's not in there? I'm looking for a 55. I'm going to start off here. It's bigger than 40. I'm going to throw away all of that. I'm going to search this tree for a 55. Well, 55 is smaller than 60. I'm going to throw away all of that. Now I'm going to search this tree containing a 50 for a 55. 55 is bigger than 50, so I should search the right subtree of 50. Well, the right subtree is null. There's nothing to the right of 50. At that point I can say 55 is not found. So right, I reached the end of the tree with no movement options. So as I do this, moving down the tree, looking for something, going left or right, based on comparing this thing to the root, if I eventually get to a point where I want to go, say, to the right, and there's nothing there, at that point I can say this number is not in the list. Well, what if I wanted to insert a 55 into the list? The process of searching for a 55 tells me if I had a 55, it would be somewhere to the right of 50. I knew there was no 55 because there was nothing to the right of 50. So guess what? That's where I'm going to put my 55. And so this is how we add things to the tree. You basically start from the root and you move left or right by comparing the value you're adding to the root, until you get to a point where there's nothing on that side of a node, and that's where you add your new number. So if I wanted to add a 25, compare it to 40, it's smaller. Compare it to 20, it's bigger. Compare it to 30, it's smaller. I can't go over here because there's nothing to the left of 30. That's where I'd put my 25. If I want to add a 35, start at the root, 35 is smaller, there's a 20, 35 is bigger, there's a 30, 35 is bigger than that, so I should go to the right, but there's nothing to the right, that's where I'm going to put my 35. And if you do this, every time you add something to your tree, it is still a binary search tree. It still has this property that at any point, everything to the left is smaller, everything to the right is bigger. And so we can still search this by playing high-low, by starting at the root and navigating down and either running out of nodes or finding the number that we're looking for. All right, questions about this? Because we're going to make it really weird next.
Very interesting. How do you invert one of these puppies?
How do you invert it?
Yeah, that's about the most common meme ever in software engineering. It's like you go to an interview and they ask you to invert a binary tree for no reason at all. Apparently, it's the most useless thing ever.
What does inverting mean?
I have no idea.
Huh, I don't know either.
Or actually flipping it, yeah. Flipping a binary tree. There's like 40 trillion libraries that do it. And, you know, in the real world, you'd probably just pull a library and do it in half a second, but...
Huh. I don't know what that means. I've never heard of flipping a binary tree or inverting a binary tree. I'd have to look that up and see what the desired outcome is.
Well, that gives me hope for interviews in the future.
Yeah, well, if it's an interview question, if it's like FizzBuzz, you know, maybe you just need to learn it because it's an interview question. But yeah, I don't actually know what that is. But I can imagine some things. But yeah, if you find a description of that, let me know and we can talk about it.
Hold on, I'll grab my Cracking the Coding interview book.
Or do it after class. Your choice. All right, so this is how we insert, right? And when you insert like this, you're still left with a binary search tree. And so you can search by, you know, starting from the root and moving down. And it's an efficient search, right? Because we may have, you know, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 things in this tree. But to search for 65, we don't have to compare all of these to 65. We start here, 65 is bigger. We go here, 65 is bigger. We go here, 65 is smaller. Null, it's not found. Right? So we chop our problem in half each time we do a comparison. And with our first comparison, we eliminated 1, 2, 3, 4, 5, 6 possibilities, more than half the tree. And that's pretty typical of what happens, ideally. Well, there's a different way to think about searching, and this is a recursive search. And this is similar to what we were doing with printing. So suppose we want to know, is there 65 in this tree? Well, we could do what we've done, keep moving down until we either find a 65 or we run out of nodes. But here's a different way to think about the problem. So let's call this, you know, search. And let's pass the root of the tree, and let's pass some number n that we're looking for. So return 1 if found, 0 if not found. Well, first thing we can do is check to see if the root's the number that we're looking for. So if root data equals n, we're done. We found our number. We can just return right there. Well, if the root is not the number we're looking for, we can compare the number to the root, and we can do the following. If n is less than root arrow data, what does that tell us? If the number we're looking for is smaller than the root node, it can only be contained in the left subtree. So all we got to do is search the left subtree and see if it's contained in there. Well, how do we search the left subtree? Let's use our search function. And if this returns a 1, the data is in our tree. And so we should return a 1. And if this returns a 0, the data is not in this left subtree. It's not in the original tree. We should return a 0. So we want to return whatever this returns. So we can just say return this. Well, if the root data is not what we're looking for, and if our number is not smaller than the root data, then our number is bigger than the root data, in which case we should simply search the right subtree for our number. And again, if this returns 1, we should return 1. If this returns 0, we should return 0. So we can just return whatever this call to search returns. And that's about 90% of a complete search function. And we really only do one comparison. We check to see if the root's equal to n. That's the easiest thing to check for. Be optimistic. Hope that the root's, the number you're looking for. And if it's not, hey, we get a friend to search for us. Hey, here's a subtree. Search this for n. Let me know what you find. And whatever that friend tells us, that's our answer. And the same thing on the right.
Well, the inverted binary tree question has been solved.
Inverting is really easy. You do recursion, but you just swap left and right nodes on each pass, still checking if the root is null like before. Okay, so swapping left and right. Oh, so mirror image.
Yeah, whenever I heard that, just in like a conversation, I always thought, well, that should be really easy because no matter if it's going up or down, it's going to be the same, ain't it?
Right. Yeah, so mirror image, I think you could do a recursive mirror function that says something like root left equals mirror root right, and root right equals mirror root left. You have to say root left before you do that. And if the root is null, then you just return null. So I think that's probably doable unless there's something really subtle going on in there. That'll be fun to think about. So here's a good recursive search function. It's got one thing missing from it though, and any time that you do recursion, it feels a little like tumbling down a rabbit hole, right? Because well, is my number in this tree? Well, I don't know. Let's check this subtree. Okay, is my number in this subtree? I don't know, let's check this subtree. Okay, is my number in this subtree? Oh, I don't know, let's check this subtree, right? And you keep calling this function on different subtrees that are getting deeper and deeper down your tree. So I want to know if 35 is contained in here. So if I have to see if 35 is contained in here, so I have to see if 35 is contained in here, so I have to see if 35 is contained in here. Eventually you got to come out of the rabbit hole, right? Now, if we actually find that the root of our tree is 35, then we say, yes, we found it, and we'll pop back up. But it's possible, we're searching for a 37, so we check this for a 37, so we check this for a 37, so we check this for a 37, and when we check its right subtree for a 37, we're searching a null tree. And so it's possible, again, that we're going to call search with a root that's equal to null, and as soon as we do this, we're going to segfault. But if we're searching an empty tree for a number, we don't have to do any work. We can immediately say the number is not found. So if root is null, return 0. Because if there's no nodes in the tree, then n is certainly not in the tree. So there's a 4-line search function for a binary search tree. So make sure you come out of the rabbit hole. And without this line, you might notice there's never anything in my function that could possibly return a 0. The only return statement is a return 1. So that kind of tells you you're missing something. But when you put this in here, now there's a chance to return a 0 or a 1. So if we step back from this and we think, how do we search a tree for n? Well, if the tree is empty, it's not found. If the root of the tree matches the number we want, it is found. Otherwise, let's look for our number in either the left or right subtree, depending on how our value compares to the root. And if we find it in that subtree, then it's found. And if we don't, then it's not found.
Which one of these is faster?
Well, that's an interesting question. This is probably going to be slower than actually moving a temp pointer from here down. Because when you make a function call, there's a lot of overhead involved. You have to sort of save your local variables and save your current context and you know, push your return address on the stack and all that sort of stuff. And certainly to simply go back up to the top of a loop with, you know, temp equals this, temp equals that, temp equals that, that's going to be a little quicker. But we're not going to really notice a big difference in speed. This is going to be fairly efficient in either case because the number of times we're going to have to do this is a function of, you know, how many levels it takes you to get to the node you're looking for or to run out of nodes. And so this is where this notion of the height of a tree comes in. And, you know, with a tree like this, we said height is the maximum number of, well, depth of a node is the number of hops from the root. So from here, 1, 2, these have a depth of 3. And this node right here has a depth of 3. And those are the deepest nodes. So the whole tree has a height of 3. Which means at most we have to do 3 comparisons, right? 1, 2, 3, well, 4 comparisons. Or we have to do, you know, 3 or 4 recursive calls. And the nice thing about binary trees is the height grows slowly. So if I have a tree with a height equal to n, how many nodes could I have in that tree? You got a rough ballpark estimate? So a height of 0. So a tree with just a root is a height of 0. So a height of 0 has 1 node. A height of 1 is this tree right here. That's got 3 nodes. A height of 2 would be this tree, which has 1, 2, 3, 4, 5, 6, 7 nodes. A height of 3 would be this, which has 15 nodes. So yeah, something on the order of 2 to the n. Perfect.
Maybe like the sum of or something, right?
So this is actually like 2 to the n plus 1 minus 1.
Oh, okay.
Right, so 2 to the 4th minus 1, 2 to the 3rd minus 1. But ballpark, you know, order of magnitude 2 to the n. And so if you want, you know, 1 million nodes, your height's probably 20. If you want 1 billion nodes, your height is 30. If you have 1 trillion pieces of data stored in a binary tree, your height is about 40. So 40 iterations of a loop, 40 calls to yourself, not a huge amount of time. So the overhead's usually pretty negligible. And that's pretty cool. 1 trillion pieces of data and you can search it with only 40 operations. Right? But this is the same magic of playing the high-low game. If you have the patience, you can play high-low with a friend. Say pick a number between 1 and 1 trillion. You can guess that number in 40 guesses, which is pretty sweet. So in the context of computer science, if you have a database with 1 trillion license plates, you could find a license plate in 40 operations, which is a whole lot nicer than 1 trillion.
That's kind of insane.
It is. It's the reason that binary trees are sort of ubiquitous with data structures.
So to create this kind of binary tree, I'm assuming you use linked lists or something like that somehow.
We can actually just use, this node structure, and we can start with, an empty list or maybe a root, and we can add by, moving down and coming to the spot where we want to add, and we'll see a recursive insert function probably on Wednesday. But you usually build a binary tree by starting with an empty tree and then adding data to it one piece at a time. And the structure of it is like a linked list, but with 2 pointers on each node instead of 1.
I see. Okay. Very cool.
Yeah. All right, so Wednesday we will look at if we have our data in this structure of a binary tree, how can we print our data so that it comes out in order? Because a binary search tree is ordered, and it turns out there's a really simple algorithm we can use, and we can make it recursive to print the contents of the tree so that the data comes out in, say, increasing order. And so we'll pick up from that concept on Wednesday, and then we'll probably start digging into some coding examples and see what this actually looks like. All right, that should do us for today. So come by office hours tomorrow if you have questions. Otherwise, I'll see you in 2:15 or office hours or next class on Wednesday. All right, thank you.
Yeah.